Welcome to Lab Life with the Air Force Research Laboratory.
Welcome to a special episode of Lab Life. I'm one of your hosts, Kenneth McNulty.
And I'm Michelle Miller.
Today we have a special guest, Kevin Rusnick, our AFRL historian, and an even specialer guest coming in just a minute. That's Dr. Harrison, or Jack, Schmitt. He was part of the Apollo 17 mission and the last man to step foot on the moon.
Well, actually, Ken, there's a debate about this. So Gene Cernan and Jack Schmitt landed together on Apollo 17. Cernan gets out first, leaving Jack as the second person to come out and therefore the last person to set foot on the moon for the first time. So he might argue that he was the last person to set foot on the moon, whereas when the mission was over, he got in first, leaving Cernan on the moon by himself, so technically he's the last person to have his feet planted on the lunar surface. So there's an argument that could be made either way, and I know the two of them had something of a kind of jocular public debate over who was actually the last man on the moon. But Cernan called his book that, so I think he at least gets priority for that claim.
So you'll be hearing from the 12th man on the moon.
In 3, 2, 1.
Welcome to the Air Force Research Laboratory, formally today for the show.
Thank you for joining us.
We know earlier you got to visit our centrifuge. Did that bring back memories at all? I don't know that you actually tested here, but during your training?
No, I never tested in the centrifuge at this facility, but NASA, by the time I was in the program, NASA had their own centrifuge, and so I had the dubious opportunity of riding that centrifuge to supposedly familiarize myself with what a launch abort might turn out to feel like. And in that case, they had estimated that the worst case launch abort would be about 16 Gs.
16?
And you could survive it.
Oh.
Well, they were familiarizing us with 12 Gs. So I actually went to a peak G of 12. And afterwards, I began to think about and read a little bit about high G loads, and I persuaded NASA, I think, that was not a good idea to take a high-value object like an astronaut and expose them to these very high G loads.
So you didn't want to go back in today?
No, that wasn't. Well, I wasn't offered the opportunity.
Oh man, we'll have to let somebody know about
they were
that.
in the middle of evaluating the undergraduate pilot training candidates for Air Force Air Training Command, I guess. And so I probably would have reneged on that one.
Don't blame there. Well, we'd like for our listeners to get understanding of the work you did as a geologist that was part of the Apollo 17 mission. Could you tell us how you got started on that pathway?
Well, that pathway to being a geologist probably started with my father, who was a geologist, and I was his field assistant as a grade school and high school student. I sort of acted at his donkey or his burro, carrying samples, and then ultimately did surveying for him before I went to college. And when I went to college, I had planned to, from high school, be the world's greatest physicist, coming out of a small school in southern New Mexico. And I very soon realized that the world's greatest physicists were sitting on either side of me in my classes and not where I was sitting. So it was a very pleasant transition to go specifically to major in geology at Caltech, and then continued that in my graduate work at Harvard.
And going from there then, so were you always on the track to eventually go to the moon, or was that something that kind of showed up on your doorstep?
No, I had not really considered thinking much about the space program until I was in Norway as a Fulbright student in 1957 when Sputnik was launched. I was actually out in the field and only heard about it over the Voice of America on shortwave radio. And when I returned to the University of Oslo, I realized that this had had a tremendous impact on the foreign students that were there. They were very much concerned about the success of the then Soviet Union with launching the first artificial satellite of the Earth. And that caught my interest. I didn't think about actually getting involved in space, but I became interested from a geopolitical point of view about it. in 1964, when I needed to get a job after getting a newly minted PhD, I contacted a man I'd met briefly a few years before, Gene Shoemaker, the famous planetologist. Just wrote him a letter seeing if he was doing any hiring, because I couldn't find a job anywhere else. And it turns out he had written me, and our letters crossed in the mail.
Oh, wow.
Because I had taken an exam, the civil service exam for the Geological Survey. And so I went out to work for Gene, and it was just a month or so after I arrived there that NASA and the National Academy of Sciences asked for applications from scientists and engineers for the first scientist-astronaut group. And I thought about 10 seconds and said, well, why not?
Of course.
And volunteered. And then spent a year with the Air Force in pilot training, and then about a year later went with the Navy for 2 weeks to learn how to fly helicopters. But in the meantime, my challenge was to bring my professional experience as a geologist into the astronaut program, while at the same time learning everything everybody else knew about flying spacecraft.
Sure.
And so that was the challenge, and ultimately paid off, and I was assigned to the Apollo 17 mission.
Yeah. And to go back a little bit, what was your time like in test pilot school with the Air Force?
Well, it wasn't actually test pilot school. It was just,
What they
call undergraduate pilot training. It was their regular program. It was a year long, and we started out in a Cessna 172 that they call the T-41, then spent 30 hours in the 172, and then 90 hours in the what was called the T-37, which was also a Cessna twin jet aircraft, and then graduated into the T-38 for 120 hours of flying. So it was really one of the more interesting parts of my life, I think, was learning to fly jet aircraft at the age of 30. Where most of the students, in fact almost all the students, were in their early 20s. So it was a big difference in age, and a big difference, I think, in learning experience. When you're 20 years old, your brain is still much more flexible even than it is at 30 years old. And you have to, as a 30-year-old scientist, I had to unlearn some habits that had formed over that 10 years, but did it successfully and really enjoyed flying jet aircraft.
Did you know that you were going to have to learn to fly when you got in the astronaut program?
Oh yes, that was clearly a part of the original program, and it was the appropriate thing to do. In fact, I think everybody who becomes an astronaut should become a jet pilot. I think it's a very important psychological as well as technical background to have, and more, I think NASA is getting back to that. For a long time, they did not require pilot training, but I think the new groups are learning to fly some aircraft. I'm not real familiar with it. No, it was a very enjoyable experience, and one technically challenging as well as personally challenging.
You had mentioned earlier today that you had spent 8 days at Brooks doing your aeromedical exam prior to training, including the centrifuge. Could you tell us a little bit about that? Because the School of Aviation Medicine is now part of AFRL.
Well, when it was at the Brooks Air Force Base, it had become the place where NASA ran their qualifying physicals. After you sent in your application to become a scientist astronaut the first time, there were 1,400, as I recall, applications that NASA received. I thought they would receive a lot more than that, but that's what they got. And they, on the basis of a FAA pilot's physical, that was winnowed down to 400. And then those 400 were asked to send in their college transcripts and I think a little bit other information. And that then was winnowed down. And this was all being done now by the National Academy of Sciences. Mm-hmm. They had a committee that undertook this further evaluation. And then from that 400, it was cut to 80. And those 80 were asked to send in an essay on what they would do if they happened to be on the moon. Mm-hmm. And it turns out I was working that very kind of project for the U.S. Geological Survey on a contract with NASA. And so I think I was able to write a fairly specific proposal on what I would do.
Did you fulfill that when you eventually got to the
Well, that actually, I think, was fulfilled by Neil Armstrong.
Okay.
He did just about everything that I think I would have recommended at the time.
Sure.
I had the opportunity to do a lot more than that because of the longer missions. And so out of that 80, the National Academy recommended 16 of us to take the physical at Brooks Air Force Base. This is a very roundabout way of getting back to Brooks Air Force Base. And that physical was really quite an intensive thing, as you might imagine, even for those days, over an 8-day period. That included a run in the Brooks centrifuge. I think they just took us up to about 6 Gs in that test. But we were instrumented with cardiovascular sensors and that kind of thing, just to see how we would react. And then out of that 16, after an interview with a variety of NASA people down at the Johnson Space Center, then Manned Spacecraft Center, that it included Deke Slayton and Dr. Chuck Berry and people like that. Alan Shepard, I think, was on the review team. 6 of us were then selected to become the first group of scientist astronaut, actually the 4th group of astronauts. Right. Out of that 6, 2, Joe Kerwin and Kurt Michael, already had qualified as jet pilots. Kerwin was a Navy flight surgeon that had just completed his carrier qualifications, and Kurt Michael had been a F-86 Air Force pilot in Korea for 5 years, or with the Air Force for 5 years. The other 4 of us had to go to undergraduate pilot training with the Air Force and learn how to fly T-30H, which was the aircraft that NASA was flying at the time. One of those 4 resigned due to some family difficulties. The 3 of us then completed that flight training and ended up at NASA in the summer of 1966.
Yeah, the one that didn't make it through the training, you mentioned the family issues, Dwayne Graveline, right? Mm-hmm. He had actually been working here at the Aeromed Lab. He had been AFRL alumni, as it were. So.
I'd forgotten that he was here, yeah.
He's one of our guys, but as you say, he didn't, obviously the standards for the astronauts were somewhat different at that time than, later on, so something like, any kind of family trouble or whatever would end up disqualifying you.
Yeah, that was a different world.
Right.
So kind of going into more of the work with NASA then, I know I read that you really helped, in terms of at least doing geological studies, helped get the training a lot better, at least kind of soup it up for future missions. How do you go about doing that?
Well, prior to my arrival at the Johnson Space Center on permanent status, the training of the astronauts in geology and science in general, but particularly geology, was more like college field trips. And, you might call it GE1 kind of training. And I evaluated this for a little while and then put together a plan by which the astronaut office would take over control of the training. They did not have control of it. It was left, unlike all the other training, which was run by the astronaut office, they had let the science side of it be run by another organization in NASA, at the Manned Spacecraft Center. And so I recommended to Al Shepard that we take control of it and run it more on a simulation base. With basically that a week a month, you would actually take people out in the field with the equipment that they would be using on their mission and work on real geological problems, but learning how to use the equipment, getting muscle memory of all that. And Al said, well, sure, go ahead. If Jim Lovell will take it on for Apollo 13, well, then fine. And Lovell was very interested. He and Fred Hayes became very good students, and their backup crew, which was John Young and Charlie Duke, then later on would fly Apollo 16. So they got involved early on as well. There was some feedback into the Apollo 12 mission with Pete Conrad and Al Bean. And so it started to have an immediate impact on the amount of understanding that the crews had about geological questions that we were trying to answer.
Yeah.
And enough familiarity that they could collect very, very good suites of samples on each of the missions. So it had a tremendous payoff for science, I think, to have this much more organized, much more simulation-based training program. And there was more time to train as well. I mean, each of the missions was a longer and longer period between each mission.
And you mentioned were you the head of this simulation? Like you helped run a lot of it, or just?
Well, I ran the first with Jim Lovell. I ran the first one, but then I was assigned to the backup crew of Apollo 15, so I was deep into a training cycle, and so I did not. But it had enough momentum with the geological survey running the logistics, and others being more and more involved in doing that. But with an overall oversight by the astronaut office, it did continue to work very well for each of the missions, much after I left the day-to-day operation.
That's great. And kind of going into that field then, so a lot of the simulations or sims you had to run to become an astronaut, can you kind of go into what some of those were, what kind of that day-to-day can almost look like?
Well, the actual geological training was very much like what a field geologist would normally do in a particular field site here on Earth. They with observation, photography, and sampling being the main activities. The training for actual flights involved hours and hours in simulators, with not only getting familiar with the normal operation of the spacecraft, the various spacecraft, but also with how to deal with anomalies as they came up. And that initially those kind of things were done by the simulator operators at both at the Johnson Space Center and the Kennedy Space Center. We had simulators at both locations. But also we would have these more extensive, what they call mission simulations, mission sims, that involved the whole network of communications, involved the Mission Control Center or the Launch Control Center. They were much more elaborate simulations, but also primarily dealing with how to handle failures of various kinds. We almost never did a regular mission as a simulation, and that was the best way to train is to have to deal with unexpected anomalies. And these simulations actually got people so involved that they forgot they were doing a simulation. I mean, it really was. They got to be very emotional issues or events. Besides the geological training, about 3/4 of our time, at least on Apollo, on the last 3 missions, was made up in a variety of ways of becoming extremely familiar with spacecraft systems and spacecraft operations.
And then we've kind of, transitioned through your journey of, back helping your dad when you first started out, getting interested in geology, to your actual training with NASA and with the Air Force to learn to fly. What could you recount a little bit of the mission itself when you went to space?
Well, our mission was targeted as, since it was a last mission, to what was thought to be the most complex and accessible location on the moon. And it was a deep mountain valley called Taurus Littoral in the northeastern part of the moon that would expose us to a whole variety of different geological phenomena, and do it in 3 dimensions because it was a deep valley. It was deep in the Grand Canyon, as a matter of fact.
Oh, wow.
Jeez.
It was an ideal place for me to apply my experience as a field geologist. And I think that had something to do with picking a complex site like that, because you would have somebody there that was used to dealing with those kinds of geological problems. The main benefit of the entire Apollo program, scientifically, probably is that we began to understand what the early history of the Earth was like. It was extremely violent. The first billion years of Earth history, extremely violent. But evidence of that has been lost to us because the Earth's so active geologically. It's almost entirely erased that early history. Or at least so far we haven't found very many clues of what it was on Earth. whereas the moon stopped much of its evolution after about 1 billion years. And so it's recorded what the early history of the solar system was like. And it was an extremely violent period. Huge impacts were occurring on the surfaces of the planets, and particularly the moon and the Earth, and about 16 times more on the Earth than on the moon, but the moon still tells us what those impacts were like. There's one basin on the moon that's 3,200 kilometers in diameter, formed by an impact. Another one that's 2,500 kilometers in diameter, and at least 40 or 50 that are 300 kilometers in diameter. Well, imagine all of that happening on the Earth. So it was it was violent. But you also know that's when complex organic molecules were getting organized and ultimately becoming self-replicating. So that's a puzzle that we're still struggling with. How did that happen? And how did when some molecules got organized, how did they survive in order to stay organized? And I think there's some answers, but nevertheless, that is an ongoing issue. But at least now we know what the question is. We didn't know those questions before we went to the moon. Also now, and just recently, we're beginning to be able to do what Gene Shoemaker, my boss at the Geological Survey in Flagstaff in 1964, what Gene Shoemaker said we were going to be able to do, and that is understand the history of the sun. Because the lunar surface is at a 10 to the minus 12 vacuum, there's basically no atmosphere, and so it's being exposed to whatever the sun's doing throughout a great deal of time. And if we can sample the debris layer properly that covers the moon, we will get a record of what the sun was doing. And we just now, I think, are beginning to figure out how to do that with the drill cores that we've taken on Apollo. And looking at the variation in solar isotopic ratios and the like is now giving us some insights into the history of the sun. And one of them is that we may now see evidence of a warming of the sun, an increase in luminosity of the sun, and therefore a warming of the Earth about the same time as what we call the Cambrian explosion. That occurred, now pretty well dated, about 540 million years ago on Earth, when the diversity of life and the quantity of life just exploded. And it's generally been assumed, and for good reason, that was because the Earth got warmer, and life likes warmth. Now I think we're seeing evidence of that having occurred in the lunar soils, having been recorded in the lunar soils. Still don't have precise dates yet on the moon, close enough that we can be absolutely certain, but it looks like we're getting close.
Wow. So going along that then, what other pieces of evidence or minerals did you pull off the moon that's really helped today? Because you said the core samples are starting to kind of find out that warming cycle. Yeah. Is there anything else you guys found that you're still developing today or has helped influence our studies?
Well, the discovery of what the solar wind, the particles coming from the sun, what the solar wind has deposited in the lunar soils with the examination of a sample that Neil Armstrong collected, 100084 if you like numbers, discovered that those resources are going to be extraordinarily valuable, not only when we begin to settle the moon, but also when we need the same resources for trips to Mars, at least to catalyze trips to Mars. Ultimately, Mars can supply its own resources, but not initially, and the moon almost certainly is the best source of water, hydrogen, oxygen, carbon and nitrogen compounds, which you can bring out of this debris layer that covers the moon. But also, there's one resource, it's a helium resource, it's a light isotope of helium called helium-3, that if we had it here on Earth would almost certainly be powering fusion power plants, because they're environmentally benign. They don't create radioactive waste. They're what we call aneutronic power plants. Helium-3 fused with itself produces no neutrons, which are the bad actors producing nuclear waste. And helium-3 fused with deuterium produces only a very few neutrons, which actually the waste that would be created would be equivalent to medical nuclear medical waste. So quite easy to handle. And so the resource is on the moon, but we don't have it here on Earth. And so the question is, will the economics ever justify bringing helium-3 back to Earth to fuel these very, very ideal power plants here on Earth? Clean, no nuclear waste, highly efficient, much more efficient than existing power plants can be.
You mentioned this is something we found after. Were you actively going in to find evidence of helium-3?
No, it had been predicted that the lunar soils might have absorbed these isotopes, but we didn't know in what quantity, whether they're absorbed and lost or what. But we knew the moon was exposed to the solar wind, and we knew that nuclear processes in the sun were producing helium and helium isotopes as well as others. But until we actually had a sample of the soil, we didn't know whether this was significant or not. And it was Neil's sample of the soil at Apollo 11, Tranquility Base, that gave us our first strong indications that this was important and potentially important for the future of humanity, as a matter of fact. And also maybe important for spacecraft propulsion between the planets, because fusion rockets are ideal for working in space. If you have the fuels, space is an ideal place for a fusion rocket because you already have the vacuum, and so being able to accelerate between the Earth and Mars, for example, and getting there in a much shorter amount of time can be extremely valuable, particularly physiologically, to avoid long-term exposure to space radiation.
And that's kind of touching on gathering a lot of the resources on the moon itself. In terms of radiation, I know you had the protective shielding, but how long were you guys allowed to stay on the surface and still stay within safe limits of the radiation?
Well, we didn't have the radiation problems in space are due to what are called coronal mass ejections or solar flares. The normal activity of the sun, like today, as a matter of fact, the sun's been very quiet for months and months and months, much longer than anybody expected. That's not much of a problem for humans. It's the big flares that are a problem, and we just assumed that risk with Apollo. We didn't have any way of within the mass capabilities that we had of protecting the spacecraft or the human beings in it from those kind of events. Now in the future, clearly we know now that there are ways to do that. We didn't know much about it at the time.
During your time on the moon, we talked about collections and stuff. Were there certain samples that really produced a lot of insight as a geologist and a scientist when we got back to process them?
Well, we added information about this early history of the Earth and how long various of these violent impacts occurred. That was added by particularly by sampling the walls of the valley on either side of us. We did gather, and we gathered the best core for understanding the history of the sun. That's where most of this solar history information is coming from right now. But most of the other samples relate more to the history of the moon and to its internal structure and to its origin, as a matter of fact. And one of the samples that I discovered, one of the deposits I discovered and the samples we brought back were of this orange soil, this volcanic ash. And this ash was produced by what we call pyroclastic eruptions, much like what we've seen recently in Hawaii, gas-driven eruptions of hot magma. And on the moon, when those happen at the surface, because of the vacuum that's there and the low gravity, the magma turns into extremely fine particles. And not like splatter as you see in Hawaii, but very fine particles that are distributed over at least 6 times farther than they would normally have been distributed here on Earth. So these ash deposits are different, but they're still understandable in the light of what we know about volcanic eruptions here on Earth. And those volatiles are very important because they came from the interior of the moon, deep interior of the moon, and they include water. About 10 years ago, a group at Brown University actually using modern, much more advanced technology than we had 50 years ago, actually found water in that ash material that we had, and that we sampled. That tells you that there's indigenous water in the interior moon, and that has two major implications. One is that it's hard to reconcile a giant impact origin of the moon with the continued presence of volatile components like water and others, many others, in the deep interior of the moon. That is a very difficult thing for the advocates of giant impact origin of the moon to model. That's a model-based hypothesis, and they haven't figured out how to deal with that yet. And I don't think they will, but we'll see. I've never felt confident that that was the right answer to the origin of the moon. Secondly, it says that the water we apparently are seeing at the poles and permanently shadowed areas may be very ancient water. These volcanic eruptions on the moon occurred 3.5 billion years ago. That's with a B, billion years ago. And we know theoretically that some of that water and some of the volatiles will migrate to the poles because they're colder. They go to cold traps. And it may be that what we're seeing is ancient water, not modern water, or not water that's accumulated since. So until we sample those areas at the poles, we really won't know. And that, even though NASA may not totally agree with what I'm saying, the samples that they would get if they went to the South Pole and sampled some of these permanently shadowed areas, or even areas that are just colder than near the equator, may tell us very quickly through isotopic analysis the origin of the water that we're seeing from orbit in those two polar regions.
You mentioned modern testing of samples that you took decades ago, and I know last week I believe there was a new core that had been, I don't want to say in storage, it's the wrong word, but
literally, it was in storage. It was in cold storage, frozen. Now the core that was opened last week is the top of the core that actually was put into cold storage.
Okay.
The core that was opened last week had not been opened, but it had not been kept in cold storage. And it had been x-rayed 50 years ago, almost. So we knew a little bit about the inside, what was in that core, but it had never seen the light of day, so to speak, until last week. Part of that was practice. There's a lot of science going to be learned from that upper core, but there's practice also in how to make sure that we do the lower core right, that may have been preserved not only in reasonable vacuum, but also in very cold. That lower core came from as deep as about 70 centimeters. And we know that there is a cold trap essentially everywhere on the moon, or at least even in the equatorial region of the moon, at about 80 centimeters. The lunar surface regularly is very insulating, and so even the diurnal solar variations don't reach that deep. And the temperature at about 80 centimeters at the Apollo 17 site, as well as elsewhere in the lower latitudes, is about minus 20 degrees centigrade. So it is a cold trap, and so volatiles may well have been concentrated there as well. So we'll see. I mean, that's the exciting part of opening these samples, and it's to the credit of the scientists and NASA who were watching over these samples early on, that they knew that technology would advance and ideas would advance, and so let's preserve some of these samples in as close to pristine condition as possible. Can't be totally pristine, but as close as possible, and then look at them sometime in the future when analytical technology has become much more advanced than it was 50 years ago.
Yeah. Well, it's very exciting. You're still part of kind of that team or some
I am.
advisory.
I'm on the University of New Mexico team that's that's one of 9 teams that are doing an integrated examination of all these samples that now are being released by NASA. That's more than just the core. There are several others as well, but the core is the most exciting one right now.
What new techniques do we have to analyze these samples that we didn't have 50 years ago?
Microscopic techniques have become extremely significant. 50 years ago we had optical, and electron microscopes were just coming into existence. And now you have ion microscopes. You have all sorts of ways in which you can examine these samples in extraordinary detail that we didn't have in those days. You also can do CAT scans of a rock. You can see what's inside of a rock now without breaking the rock, and so that wasn't possible 50 years ago. And we can do much more precise isotopic separations of mass spectrometry today than we could 50 years ago. So it's just like almost all technology, it has matured and become much more precise than it was then. And 50 years from now, it'll be even better, almost certainly. So, and these rocks will still be around. I mean, the Apollo program never ended for science.
Right.
It really didn't. It'll continue. These rocks and soils will continue to be analyzed. It's a very active community, and lots of grad students involved, and I see no reason why it won't continue.
Would you have thought that 50 years from then we'd have no new samples from the moon because we haven't been back there to get any new ones?
Well, I didn't predict it would be 50 years, although I guess you can explain it in many different ways. It's nice that at least this administration is beginning to think about getting back and has a plan to get back. Now, whether that plan is going to be funded properly, whether it's going to be organized properly, is something that we'll just have to wait and see.
Yeah, I know I think when you were actually on the surface of the moon, President Nixon read a proclamation where he said to the effect that this was the last time we were going to be on the moon in this century. And I know people back at Mission Control, I think at least, were a little bit kind of stunned by that because they obviously knew Apollo was ending, but I don't think anybody really believed that 30 years from then we still wouldn't be back again. So
we didn't know. My objection was he didn't have to say it.
That's true. Once you say it, it adds a little bit of finality to it, doesn't it?
Yeah.
So are you excited about the future of space exploration?
Well, at least there's a lot of interest. I mean, there's private sector interest, there's international interest. The administration has realized the geopolitical importance, I think, of space more so than in the past. And so, yeah, I think it's a great time for young people to get involved. NASA has to, and others have to create an environment in which young people can be involved. I emphasize young people is because you got to go back and realize that Apollo was a young person's program. The average age of engineers, 400,000 engineers in NASA and in the private sector, was in the 20s. And we need to get back into that kind of environment. Young people bring imagination and stamina and patriotism and commitment that after you've been through a few decades, you probably don't have nearly as strongly as you do when you're in your 20s. So I think that's a very, very important component of any future program. And the private sector has realized that. If you look at the average age of engineers at Blue Origin and SpaceX and others, they're young. They're in that same range that NASA was during Apollo.
You have any advice for those young geologists, engineers, scientists that might go back to the moon or Mars or anywhere else?
Well, get as broad an education as you possibly can. Emphasize mathematics. That's the tool of the future, in my opinion. Whatever happens, you need to have that math background. And just keep plugging away, and maybe you'll have the chance.
That's great. Yeah, you never know.
Don't depend on luck, but be ready for it when it occurs.
I was Googling you, to be honest, to see what you've been involved in. You've been involved recently in some research about, I think it was like a landslides in Mars or activity on that planet.
I'm working with a team in London, a scientific team under Tom Mitchell, who is a landslide avalanche expert. And I'm working with them because I wanted them to examine the avalanche that we've identified in the valley of Taurus Littoral, where I was and I explored, and see if we can't get more information based on their modeling techniques into which we then fit the actual field data that we've collected and the sample data. And so that is part of what I have been trying to get this group to do, and they're working on it. They had started out working on Mars, and actually Tom Mitchell did some fantastic work here in the United States on some big landslides, and that's how I ran into his name. And now his team is looking at this, what we call the light mantle avalanche in the Valley of Taurus Littoral. That is debris that's come off that high mountain that I mentioned, that 7,000 foot high mountain, and spread out across the valley. And we're trying, probably about 75 million years ago is when it came, and it may have been activated by an actual fault, a moonquake,
Okay.
that caused that avalanche to flow. But I want to see if we can't get more information about what the dynamics of avalanches are, dust avalanches are in 1/6 gravity and in a vacuum, and how they're fluidized, how volatiles are released in order to keep them fluid enough. Think of a snow avalanche, for example, with very fine particles, and it gets fluidized. If it gets launched, it traps air, and air gets in the avalanche, and that's right why they move so quickly, so fast, is that they're really riding, in a sense, on a cushion of air. And there's very low friction involved in that. And trying to see whether avalanches on the moon and potentially on Mars, how they operate. Can we model that? Can we do experiments to better understand how that happens? It's not such a big deal on the moon, except when we get to, if we can understand them on the moon, it's going to make it easier to understand these on Mars. And some of these on Mars may contain a great deal of ice, and so they become important resource sites on Mars, where they're not going to be that on the moon. But still, it's all a question of progressive science, of increased understanding of a particular type of phenomena, namely landslide or avalanche type phenomena.
Okay, so then by understanding, I guess, how that happens, you're thinking that it could lead you to resources to sustain time on a planet?
On Mars, yes. On the moon, it's mainly sort of a building block. If we can understand avalanches on the moon, we can probably better understand them on Mars.
Makes sense.
And touching on a lot of what you've said, what would you want if you had more of a say in, let's say, the next moon mission? What do you think the next objective should be when we get back to the moon?
Well, as soon as possible, we should be exploring the far side. And this large basin on the far side called South Pole Aiken, which is 2,500 kilometers in diameter, is a very complex basin, but it's one and it's going to take quite a bit of, I think, a number of landings to fully understand what it's going to tell us about the moon and about these huge impacts that were occurring very early in the history of the solar system. The moon records 2 very clearly, in my mind, probably 5 not so clearly, and Mars has several as well. But of course, we don't see any sign of them here on Earth. And understanding those, the mechanics and the consequences of such an impact on the moon is going to help us understand what may have been the consequences here on Earth when they occurred. For example, do they relate to the formation of the first continents? And there are arguments, complex arguments, of why that might be true. But until we fully understand these basins on the moon, it's going to be hard to say just what the consequences were of such a large impact here on Earth.
If I can continue the comparison between the moon and Mars, there's something of a debate in the space community about how much of an analog learning on the moon, learning how to operate, how to live there, relates to doing the same things on the moon. Given your experience, is going back to the moon a good analog for developing technologies and learning techniques for living and operating on a body that's not the Earth?
It's a great place to learn how to do that, and for generation or 2 or 3 to develop how to manage risks in deep space. We haven't been in deep space for almost 50 years, and it's going to take another generation or 2 before we get to Mars. And so we're going to have to relearn all of that, and particularly relearn how to manage risks. That's the whole business of working in deep space. Now, you shouldn't become risk averse, but you should certainly learn how to manage the risks that are there. They don't go away, right. And they haven't gone away. In spite of the advancement of technologies, the risks are still there, but the advancement of technologies gives you more techniques on how to manage those risks. So I think the moon is a critical place to do that for operational risks as well as testing equipment, testing various ways to do that, to actually operate in deep space. For one thing, remember, Mars is a long way away, and that means communications are not going to be what they were during Apollo. You can't have a mission control watching over your shoulder as you land on Mars. Right. It's all going to be in the spacecraft and in the people that do that. And you can learn to do that on the moon. You don't have to go to Mars to learn how to deal with very long periods of no communication. Moon's only 3 days away. Let's take advantage of it.
Right. And you're close enough that if something serious does go wrong, you're able to get back home.
Well, I hope so, yeah.
Yeah, right.
But you also have to deal with those kind of situations. You'll have to learn how to deal with that. One of the things I think Mars will require, instead of doing what we did in Apollo, and that is if you have a problem during landing, you would abort to come home. On Mars, when you're at Mars, you're going to abort to go to land. And that changes the whole engineering concept of landing on a planet. If you're going to spend all the resources, take all the risks to get there, you're going to abort to land and figure out what went wrong once you landed. So that means you're going to have more redundancy, more backup systems, so that you can indeed abort to land and then figure out what the problem was.
Okay. So given your training and preparation for walking on the moon, how did that compare with the actual operations on the surface? Were those techniques you learned, were they valid? Were they helpful for once you got on the surface?
They were helpful in learning how to handle tools, how to take pictures quickly, how to do sampling. But as far as becoming familiar with 1/6 gravity, there's no way to do that. You can get 30 seconds of it maybe in an aircraft, parabolic flight in an aircraft, right. But that doesn't teach you that. You learn that very quickly once you're there. Human beings are very adaptable. We've got to remember that.
Right. So what was your first impression of 1/6 gravity when you step off the ladder on the LEM and hit the surface? Well,
and starting to walk, it was like walking on a giant trampoline. You're only 1/6 your weight, your same mass, but 1/6 your weight, and that enables you to really to operate very easily. The only physical difficulty I found in working, even in the A7LB pressure suit that we had, spacesuit that we had, was with the gloves. The gloves are pressurized gloves. They're at about 3.7, 3.8 pounds per square inch. And so every time you want to pick something up, you have to squeeze against that pressure. You have to do work. And that wears these forearm muscles out very quickly if you're not disciplined about it. And so that was the physical difficulty of working on the moon with the gloves. And I hope NASA in their new suit work is putting the resources into glove design and spacesuit design that will be important to allowing people to operate for multiple days, beyond 3 days, as we did on the moon. The other thing NASA needs to do in that suit design is figure out how to reject dust and not carry dust into the habitat.
So what advice would you have for future trainers in terms of setting up a valid training program for those that are going back to the moon?
Well, I think basically you do the same things that we did with obviously use different equipment and things like that, but I wouldn't worry about training to work in 1/6 gravity.
Really?
I would do better muscle training. I'd get trainers. In fact, the space station assemblers, the astronauts that built the space station, did have specialized training, muscle training for these forearm muscles, and they did much better than we did. We exercised, we did things, we knew it was an issue, but we didn't have the expertise, nor did we hire the expertise in order to get these forearms in the kind of condition they should have been.
Yeah, you'd have thought by the time your mission came along, the last one, that the previous missions would have translated that to you guys and say, hey, squeeze some more tennis balls or something.
But it's going to take more than that. We did all that.
Yeah.
I mean, we knew it was an issue, and so we did a lot of gripping and things like that, but it wasn't enough. You need specialized trainers, and the space station assemblers did get that specialized training, and it made a lot of difference. And it particularly necessary for them because their suits were at higher pressure than ours.
Right.
Yeah, I think that can be solved. Those issues can be solved, but it's going to take some more thinking about it, I think.
You mentioned the dust being a problem. I was looking at pictures and everything looks gray until you see that it's actually a color photograph because you've got a scale of I mean, it's just amazing. That's all dust. What did you experience on the moon with regards to dust?
Well, anytime
environment?
you pulverize almost any rock, it's going to turn gray.
Yeah.
And any group of rocks, as they get mixed up, it turns gray. And half the surface material of the moon is less than 100 microns in average diameter. So it's very fine dust, very fine dust. And 1% is less than a micron in average diameter. So, and that's probably the biggest that is a potential physiological issue, and one in which a cottage industry is developed to deal with. And my argument is that you solve it with engineering solutions. Just don't let dust into your habitat. Don't breathe it. And that's an engineering issue, not a physiological issue, of how do you keep dust out of your habitat. The easiest way is to keep the suits out of the habitat. And in fact, there have been some work at the Johnson Space Center on getting into the suits through the wall of your spacecraft. And that's a good solution. Ultimately, though, you've got to refurbish those suits. You've got to maintain them. You can't take hundreds of suits to the moon or Mars. You're going to have to use the suits you have and design them so they can be refurbished and maintained for long periods of time. Our suits were qualified they said, for 6 actual EVAs, excursions onto the moon. I think they could have done that, but they were starting to wear it. The gloves were wearing, the backpacks were wearing, and the like. And so we really need to think very hard and put probably much more resources into suit design than we have in the past. Now, NASA is designing a new suit. I'm not familiar with what they're doing. I don't know how much they're willing to invest in those suits, but it's very, very important. If you're going to take human beings into space, you need to make sure you're using all their capabilities and using them very efficiently. Otherwise, it's not quite clear why you do it. Now, we took our brains and our eyes into space, but we sort of neglected really being able to use our hands as efficiently as we should have. In fact, it was not very efficient at all. One thing is that as you reach in the glove and against the bladder, you would lift the fingernails. And everybody ended up with sore nails, blood in the quicks here of your fingers. No matter how closely you clip these nails, you still, that wear. And I even wore nylon liners, and I still had that happen to me. My partner on the moon had a very difficult time with abrasion. And he didn't wear liners. He probably should have. But I think his hands had swollen over what the gloves had been fitted for. And so he was getting very bad abrasion on his fingers and hands. So there's a lot yet to be done to make these suits really the way they ought to be in order to maximize the human potential in space.
Yeah, so much design.
Yeah, and that's an interesting angle I hadn't really thought of before. In your habitat, do you guys have what medical supplies do you have if you needed help with that?
Salve.
Yeah.
Yeah, that was it.
That makes sense.
We had some. And
at least get some to help.
Yeah, and my partner really had to use that on his. I did not. There was nothing. I mean, you just keep your nails clipped, and that's about it.
And talking about a lot of these samples and the moon rocks you gathered beforehand, how familiarized were you before you actually went on the mission with what had been gathered beforehand?
I was quite familiar, and we tried to familiarize the other guys as best we could in the time available. But I spent a fair amount of time working on the samples and making sure that I knew what had been found before. And if you listen to the transcript, every once in a while I will read the transcript. I will mention some sample from Apollo 12 that this looked like.
That's cool.
And today I can't remember what that sample is, but then I knew.
Fair.
Then I knew.
And I know I read online as well, I won't get the name right, but there was a specific mineral or a rock you found that kind of helped showing that the the moon had a magnetic sphere, or like actually had a.
Well, through a leap of geologic interpretation, some samples that we obtained at Camelot Crater, on the rim of Camelot Crater, have been determined, in my mind at least, to be more or less in place. They've rotated a bit through a colleague of mine, a retired astronomer who loves to manipulate photographs. We were able to reorient those samples down, and then an expert in paleomagnetism at MIT, Ben Weiss, and was able to actually get what he calls a paleo orientation of the magnetic field from that rock, and it's consistent with that rock having been level at one time and giving a orientation of the magnetic field as a dipole, much like on the Earth, with the poles roughly in the position of the current rotational poles of the moon. So that's one of the, I think that's the only sample that has come back from the Apollo missions that we've been able to do a paleo orientation of the lunar magnetic field on. You'd like to get more, and we have some other ideas about how to do that from the Apollo 17 samples. They're well documented. We took very strong stereo photography and everything of each sample as we took it, so you could reorient these samples as they were actually on the moon. And that was a plan actually put in place by Gene Shoemaker with the Apollo 11 mission. It was to always try to document the position of the sample that before you took it, and then you take a picture afterwards just so you can tell what sample came out of the picture. And so we have beautiful documentation. And there are new techniques, back to new techniques, analytical techniques in software that enable you to reorient samples much quicker and much more precisely than we thought we could when we had that gnomon, the color chart you had. That's actually a gnomon that was invented by Shoemaker again in order to control the orientation of these photographs, because the rod is on a gimbal and the rod seeks the local vertical, so that gives you local vertical. The shadow gives you the azimuth, so that the camera's pointed at, and then you have scale in it too, centimeter scales. So you can actually use that to create topographic maps of a site that in which the sample occurs. Now though, you don't even need to have that. You can use shadows. There's software that allows you to use just the shadows cast by the rocks, if you get enough of them statistically, in order to do that same thing.
That's wild.
And my colleague Ron Wells, who's the retired astronomer I mentioned, has become a real expert in doing that now.
Wow.
Yeah. And he was the one that oriented the sample that I mentioned for a paleo orientation of the magnetic field. I did the geology work and said, yeah, if you move this down into horizontal, it'll probably give you the way that sample was originally. But I had no idea how to do it.
I mean, hey,
and he did.
Covered every angle, so you got it covered.
Not even. Yeah.
So
I think the big thoughts and let other people do the hard work.
See, that's teamwork. Worked out. So with that, then, how many cameras did you bring with you to the surface?
Two
Okay.
Hasselblad cameras, electric drive. They were 70 centimeter focal length, I believe, if I remember correctly. 60 or 70, I think, is what we had. The magazines were quite large. I think it was 150 frames on the color film, and 170 on the black and white film. I had a black and white film in my camera. Commander had a color film in his camera.
So being a geologist, then, you were pretty. You knew what pictures you were looking for. Would you say you were an avid photographer, or just skilled due to your trade?
No, it was practice. It was just all these trips, and the camera's mounted here, and we got very good at pointing that camera just with your body.
Yeah, just make sure.
Yeah, and it was, you just pointed your body, and because of that training, it was automatic. and the pictures are really quite good. They're pretty
Yeah,
well
pretty
taken.
popular.
I happened to bring one of those pictures with us, one of the probably the
Well, now
famous
that
shots.
one wasn't easy.
I watched the video of you guys actually shooting these.
Well, the commander did that, and he had. I could not have gotten into the position he did in order to get that picture.
Yeah, it looked like he was having to kind of squat down a little bit just to really.
He was a little bit taller, and he could bend his suit a little bit more than I could.
Okay.
To do that, and but that was not an easy picture to take.
And so was he? The cameras didn't have viewfinders, is that correct? Or they did?
No, you just pointed. No, you just pointed.
Okay, yeah. So I mean, to be able to get this sort of composition where you have you and the flag and the Earth overhead, I mean, that's remarkable.
Yeah. Well, it took several, and that's the best.
Hey,
That's your
Indeed
favorite.
it is.
gotta
Yeah.
have it covered.
No, that's an unusual photograph. Most of them were just straightforward, move the body, get stereo just by stepping to the side, and it worked out very well.
Well, unfortunately, we're out of time, but we've learned a lot today. It was a happy note to leave on. But thank you so much for your time and sharing your thoughts about the future of space and your experiences there.
Well, thank you for the opportunity. Wish you all well.
Thank you.
Thank you.
Thank you. Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.